Back. All right. Can you guys hear me? Hello?
Yes, Professor. How you
Okay.
doing?
Yeah, sorry about that. My internet went out in the middle of my last lecture, so I've been on the phone with Spectrum this whole time trying to get them to put it back up. It looks like I got back right before this lecture. We can set up here. Hey guys, if you're just joining, I need a minute to get set up. My internet went out in the last lecture, so I had to call Spectrum, but it looks like it's back. How's everyone doing today while I'm getting set up here?
Good. How about you? Other than the
How are you?
internet stuff.
It's good. Yeah, it's a little surprising. Suddenly I was talking and then all of a sudden Zoom crashed on me and then all my internet went out. So it was a little bit surprising in that sense, but glad it's back. All they had to do was just kind of reset my router apparently, or reset my modem from there, which is fascinating because it's all automated now. So I didn't have to talk to anyone, which I guess is nice because I didn't have to wait on hold for a long time. But it's interesting that it's all of this is kind of automated, and all I had to do was just talk to robots the whole time. Okay. All right, so we're in our third week, right? So this is week 3, lecture 1 of EGME 442. Right? Right. So we have our first homework assignment is due tonight. So, you know, I know I've gotten quite a few questions on that homework assignment, but, you know, hopefully everyone is kind of working through it. Remember, you know, for this class, that homework is graded on completion. So, you know, if you, you know, if you can't figure out a problem, just give it your best shot. You know, as long as I can see that you gave a pretty decent effort at it, that's, you know, that's good enough for me in order for you to get full credit. But, you know, anything that you don't get, remember to make sure that you go check the solutions afterwards, because, you know, that stuff's not going to go away. You know, we're still going to use it. You know, obviously you're going to see it on the midterms, but, you know, all that information is good to know for, you know, the final project and everything like that. Okay. Okay. So are there any questions on the homework that I can answer before we, or anything else that we've covered so far before we get started? All right. All right, so there's no questions. Oh, sorry, something in the chat. Yes, you can. Yeah. All right, so if there's no questions, let's go ahead and pick up where we left off. And so last thing I think that we were doing last Thursday was doing our review on fluids, okay? And so today we're gonna pick up kind of right where we left off there. And I believe where we left off one was, you know, Navier-Stokes, okay? And so the first thing that we're going to do, I'm going to be writing the learning objectives in real time, is we're going to use the Navier-Stokes equations to compute velocity distributions in a rigid blood vessel. Okay. Right. And so this may or may not have been something that you've seen before in a previous fluids class. It depends on who you had for fluids. But what you'll see is that you know, we'll be using the cylindrical version of Navier-Stokes. Okay. we'll start with the Cartesian version because I think everyone should have seen that one before, just to kind of explain what all the different terms mean, and then we'll use that as kind of a launching point to actually start to do cylindrical Navier-Stokes. Okay. All right. So let's go ahead and get rolling with that. All right. And so if you remember from your previous fluids classes, your Navier-Stokes equations they represent the conservation of mass and momentum in a flowing fluid. Okay. Right. Because ultimately what we want to do is we want to solve these Navier-Stokes equations to solve for the velocity field, right? And we know from last time that if we know the velocity field, we can learn everything that we can about the fluid's motion. Okay. All right. So let's write down the Navier-Stokes equation. So I think this is kind of exactly where we got cut off. So let's start with this guy. And so this is kind of the first part of Navier-Stokes, and I think the part that a lot of people forget about. And so this equation right here represents conservation of mass for a flowing fluid. Okay. All right. And so let's define all these terms here. So U here is going to be the fluid velocity in the x direction. Right. V here is the y component of velocity. Right. And Z here, or W is the z component of velocity. Okay. Right. And so basically the conservation of mass states that if you take the derivative of each of the different velocity components with its respective coordinate, right? And so you take the x derivative of u, the y derivative of v, and the z derivative of w, and then you add all those together. And then by conservation of mass, all of these guys should add up to 0. Okay. And so this guy is very much a part of Navier-Stokes. So he doesn't really get that much credit because he doesn't look as scary, but he's just as an important of a member. Okay. Okay. And so the common name for this equation here is the continuity equation. Right. And so if you see, people refer to the continuity equation, all they mean is basically just the conservation of mass from Navier-Stokes. Okay. All right. And so there's that guy. Okay. And one important thing to note is that in order for us to use this form of conservation of mass, we had to assume that the fluid was incompressible. Okay. Right. Because this equation right here isn't the only equation for conservation of mass in a fluid. Because if you assume that the fluid is compressible, like you have like a gas or something, then you have to also account for changes in density. Okay. But if we assume that the fluid is incompressible, what we basically mean by that is we essentially mean that the density is constant. Okay. And this assumption is pretty valid for any fluid that's in the liquid state, right? And so you're talking like water, like honey, like blood, right? And so generally for anything that's in any fluid that's in the liquid state, we can generally assume that it's incompressible, and that's usually a very fair assumption, okay? And so since we're mostly dealing with blood flow in this class, we're going to make that assumption of incompressible, okay? Intuitively, what you kind of think of it is that, you know, it literally means what it says in its name. So if you take like a certain volume of fluid, you can't compress it into a smaller volume, right? And so if you have like a balloon of, you know, water, you can squeeze it all you want, and it's going to change shape because it's a fluid, but its volume is never going to change, no matter how much pressure that you apply to it. Okay. All right. Any questions on this? Okay. All right, so that's a conservation of mass. Now let's start talking about the conservation of momentum. And so I'm not going to go through the derivation for this equation because, you know, again, this is not a fundamental fluids class. Instead, what I'm going to do is I'm going to write down the equation, you know, here, and then we're going to talk about how do we actually interpret it, right? Because to me, I think it's important to, you know, not only know how to use these equations for your engineering analysis, but also to really have a good physical understanding or physical intuition behind what all of the different terms represent. Okay. All right, so let's go start with Navier-Stokes, conservation momentum. Okay. And I'll note that, you know, I'm only going to write one component of the momentum here. Oh, question, m du dt. What do you mean by that question?
I might be getting it confused, but I thought that that's how you started this equation. Like
oh, okay.
Yeah. To the Navier-Stokes.
Yeah.
Like
right. So there's different forms of this equation. So there's a form of the equation where you multiply the entire thing by density, but I'm going to write a form where you divide the density throughout this entire equation. So I like this form better because the left side is kind of by itself. But there's other forms where, you know, this entire left-hand side is multiplied by density. Yeah. Okay. Okay. So that's everything on the left-hand side. Next, we have 1 over rho times the pressure term. Then we have gravity in the x direction. Okay. Then we have the viscous term. Okay. Right. And so this monster of an equation here, this is probably the Navier-Stokes that you've either come to know and love or know and hate from your previous classes. Okay. All right, so let's go through each of the terms here and let's talk about what they physically represent. Okay.
That's mu over density, right?
Yes. So that's mu over density.
All right, thank you.
Mm-hmm. Yeah, so we have viscosity over density. All right. And so this first term that I've circled in red right here, this is the only term with time in it, right? And so you don't see time appear anywhere else in this Navier-Stokes equation, right? And so what this term represents is what's called the unsteadiness. Okay. Okay. And so what that means is that this term basically represents how the velocity can change with time. Okay. Right. And so, you know, if you stand still at a fixed location in a fluid, you can observe changes in velocity because, you know, velocity in a fluid can change with time. Okay. Okay. Next, let's look at this next batch of terms. And so all these guys belong together. Okay. And so these are the convective terms. Okay. Okay. The three amigos of convection. Okay. That's what I like to think of them as. And so what these terms represent is how velocity can change with space. Okay. And so if you're, you know, if you have a flowing fluid and you move spatially from one location to another, you can observe some changes in velocity, right? And so, you know, I'll give you just a very quick example through, you know, from which we can observe this in blood flow, right? And say that you have flow in a blood vessel, right? But let's say that there's some disease in this blood vessel, right? And so let's say that we have some plaque, or in other words, you know, some fatty cholesterol that that deposits onto the sides of the vessel, okay? And so you have blood that's kind of flowing through this vessel with disease, right? And so as the blood goes from here, which is a relatively healthy section of the blood vessel where there's no disease, and then you compare that to the velocity here, which is in, you know, right at the neck of the disease, you're going to observe some very different velocity, right? And so in the healthy portion, you have kind of a lower velocity, right? Because over here, you know, you have, you know, a larger cross-sectional area. Whereas if you compare the velocity to, you know, going through the disease, you'll have a much higher velocity there because just the opening is just a lot more narrow. Okay. And so this idea that, you know, just by moving in space, not really, you know, changing in time, that you can observe some velocity differences, that's encapsulated there within those convective terms. So that's essentially what they represent. Okay. Mathematically, the convective terms are usually the biggest nightmare to solve. And so, you know, Navier-Stokes, the reason it's so difficult to solve is precisely because of these green terms, because they're nonlinear, and they're just generally very scary. So, you know, most of the time when we're solving things by hand, we're going to ignore these terms right here. But, you know, in the full Navier-Stokes, this is kind of what they represent, that, you know, you can have changes in velocity just by moving from one place to another. Okay. Okay. Any questions on this so far? Okay. And so that's everything on the left side of the equal sign, right? And so everything on the left side of the equal sign represents changes in velocity in some way, right? And so we have the unsteady term, which represents changes with time. And then we also have the convective terms, which represent changes in space, okay? And so everything on the right of the equal sign in Navier-Stokes, you can kind of think of those as forces, or ways that, or, you know, forces or stresses that can cause changes in velocity, right? And so everything on the right here, you can almost think of as like actors, or, you know, or external effects that causes changes in momentum. And so the first one that we'll look at is the pressure term, which I've circled in blue right there. And so what the pressure term represents is how pressure forces can be used to drive fluid flow. More specifically, gradients in pressure are used to drive fluid flow. Okay. And so this is going to be really relevant for blood flow, because in blood flow, you know, your main driving mechanism is your heart. And the way that your heart works is that when it pumps, it causes, you know, high amount of pressure in your system, and that causes, you know, the blood to circulate through. Okay. And so this pressure term is going to be very relevant for us. Okay. Next, we have G. And so G here is going to be our gravity term. Okay. And so our gravity term just represents how flow can be driven by gravity. Okay. And so you know, flow is or fluids are just as susceptible to gravity as any other you know, any other object. And so the force that's imposed by gravity can also cause flow. Okay. Okay. One really interesting application of this in cardiovascular fluid mechanics actually has to do with you know, with really tall animals, right? And so actually, you know, I saw this in kind of a YouTube video recently about giraffes, right? So giraffes are very, very large animals, right? And so as you can imagine, the heart has to work really hard to drive the flow all the way up to the head of the giraffe, right? And so there's a lot of really interesting fluid mechanics that happen when the giraffe bends down to drink some water, right? Because if you can imagine, you know, all that gravity force is suddenly going to go towards the giraffe's head. And if, you know, there's very special mechanisms inside the giraffe's head that can temporarily store blood flow so that when the giraffe bends down to drink water, all the blood doesn't go rushing to its head, right? And cause it to be lightheaded and cause it to faint and, you know, which is all the bad stuff. So there's a lot of really interesting fluid mechanics inside giraffes that, you know, I admit that I'm not that big of an expert in right now, but I think would be really, really interesting to study someday. Okay. All right. Right. So that's going to be next. So after we go through these terms, we're going to talk about assumptions and how we can actually cancel out these guys. Yeah. Okay. All right. So question. So what about nanomachines in the bloodstream? And so that is also a very interesting topic that I would have to study more to before I can give a good answer to that. But there are a lot of really you know, interesting applications for all these guys. Okay. And now let's go through the last set of terms right here, which I've circled in orange, and these are the viscous terms. Right? And so all of these guys are grouped together because they represent how viscous forces can also affect velocity distribution. Yep. And so viscosity actually is going to be very key here because it's one of the main terms that we're going to keep after we apply all our assumptions. Okay. And kind of the net effect of viscosity is that it kind of forces our velocity distributions to be smooth. Okay. Right. And I'll explain kind of what I mean by smooth kind of, you know, later on. Okay. So before I get there, are there any questions on this?
So Professor, is it mu over P or is it rho?
It's mu over rho. So that rho there is density. And so
Okay.
the way I kind of differentiate between P for pressure and rho is that I give P a little ponytail. Right? And so the P kind of has a little thing on the back there. So if you see P without a ponytail, then that should be density. Okay. Any other questions on this? Okay. All right, so let's talk about some assumptions that we can make in order to simplify this equation. Okay. All right. And so, you know, the reason we use assumptions is because, you know, the equation that we have on the previous page is way too big and complex to solve by itself. Okay. So we usually cancel out a bunch of terms so that we can, you know, actually solve this guy. Right? And so we apply a lot of assumptions, right? And so I'm going to list 5 right here. which are, going to be, you can kind of assume going forward, whenever you see a, Navier-Stokes being solved, these are kind of the assumptions that we're going to be working with, okay? So first of all, we're going to assume we're going to have steady flow. Okay. And so what that assumption means is that nothing is going to change with time. Okay. And so if nothing changes with time, then any derivative with respect to time can be set to 0. Okay. And so if we go back to our previous equation right here, this means that we can just cross out this unsteady term and just kind of get rid of it. Okay. Right. And as as we learn more about the cardiovascular system, we'll see that this is actually not a great assumption, because blood flow in your cardiovascular system is pulsatile, right? So it's actually changing regularly, with every heartbeat. Because with every heartbeat, your heart is basically pushing out blood, right? And so your blood flow is actually going to go up and down. But for now, just to kind of as a starting point, we'll assume that the flow is steady. Okay. Right. And so the next assumption we've already talked about. And so this is the incompressible assumption. And this basically allows us to assume that the density is constant. Okay. And so, just like we mentioned before, as long as you're talking about a fluid in a liquid form, this is a very reasonable assumption to make. Okay. All right. And so the next assumption that we'll make is that we'll assume that the flow is 1D, okay? And what this assumes is basically there's only going to be one component of velocity. Okay. Because you saw on the previous pages that we have 3 components of velocity in 3D, and so in Cartesian coordinates we have u, v, and w. And so under the assumption for 1D flow, we're going to set 2 of those to 0. So we're going to set let's say v and w to 0. Okay. The next assumption that we'll make pretty commonly is that we're going to ignore gravity. Okay. And so if we ignore gravity, that means that this gets rid of our gravity term. Okay. And so this assumes that gravity is negligible. Okay. Right. And so it's not that gravity is not there. It's just that, compared to some of the other forces in our problems, like the pressure force, gravity, relatively speaking, is not that big. Okay. All right. And so one other assumption that we'll make, and this is unique to just cylindrical Navier-Stokes, is we're going to assume that the flow is axisymmetric. Right. And so what that means is that, once we move into cylindrical coordinates, we're going to have one of our variables to be theta, which is going to be the polar angle, right? And so what axisymmetric means is that, we're not going to have any dependence on our solution with theta. Okay. Okay. And so any derivatives that have to do with theta, we're going to set that to be 0. Okay. Right. Okay. And so under all these assumptions, generally the Navier-Stokes equations become a lot simpler. Okay. And so just to kind of give you a preview, so I won't go through all the motions for the Cartesian case, but under all those assumptions here, basically what ends up happening is that we cancel out all the convective terms because we know that those are too scary to solve. Right? we end up canceling the gravity term here, okay? And we also end up canceling all of these terms as well, okay? And so the only thing that we end up left with is one term for the viscous contribution, right? And so we usually have a second order derivative that comes from the viscous term. And we also have the pressure term that stays, okay? And this makes sense because, you know, the pressure term is, the pressure is ultimately what's going to be driving our flow. And so we need to keep it in our equation, okay? And so through applying all those assumptions and applying those assumptions to the, you know, continuity equation too, we end up with an equation that basically looks like this, okay? And so we have basically just a 1D equation with one velocity component and one varying variable, okay? And then that's a differential equation that we can actually solve for, you know, just using just elementary ODE stuff. Okay. All right. Any questions on the assumptions here? Okay. All right. And so now let's talk boundary conditions, right? And so we're not ready to solve yet because we need to talk about how we're going to constrain our velocity distribution. Okay. All right. And so, you know, just to kind of give you just an overview, our boundary conditions here, they describe how our blood flow is going to be, how the behavior of the blood flow is going to be at the extremities of our domain. Okay. Okay. All right. And so in cylindrical Navier-Stokes, there's one boundary condition that's pretty obvious, and then one boundary condition which is not so obvious. Okay. So let's start with the obvious one first. And so the obvious one that we need to apply is is called the no-slip boundary condition. And what the no-slip boundary condition states is that the blood that's in contact with the vessel wall basically has to stick to that vessel wall, right? So that's what no-slip means. And so any velocity that kind of, you know, is in direct contact with the wall has to match the same velocity at that wall. And so the way that we prescribe this is that we say that, you know, the velocity at the radius of the vessel has to equal to 0. Okay. Okay. And so if we have a blood vessel and we say that its radius is big R, okay? And so mathematically, the way that we formulate this boundary condition is we say that U at big R is equal to 0. Okay. Right. And so this is not that different from, you know, when you solve your Cartesian Navier-Stokes and you had kind of a stationary surface, right? And so if you remember from those cases, when you solve your Navier-Stokes equations, you force the velocity to be 0 at those solid surfaces. Okay. Okay. And so that's one boundary condition. So that one's kind of obvious. The other boundary condition that we have to apply, which may not be as obvious, is that we have to assume that our velocity distribution is symmetric. Okay. Okay. And so what that means basically is that as you go from one wall of the vessel to the other wall, you should see kind of a symmetric velocity profile. Okay. So let me kind of draw an image here to kind of show that. Because I think it's a bit easier to show with an image. Okay. Okay. So I draw kind of a dotted line here to represent kind of the middle of the vessel. Okay. The middle of the vessel is when little r is equal to 0. Okay. And so little r here is our radial coordinate. Okay. And so we have little r that's going like this, like that. Okay. And so when I say that the velocity profile has to be symmetric, that means if you go on one side of the dotted line versus the other side, you should see the same velocity profile. Okay. Right. Another way to say that is that the velocity has to reach a maximum at the center of the vessel. Okay. Right, because if it reaches a maximum at the center of the vessel, then both sides there have to be the same. Okay, and so mathematically, the way that we express this is we say that du dr at r is equal to 0 has to equal to 0. Okay.
Professor?
Yep. What's up?
If you have to say, for example, or for a vessel, say we have like our veins or something, right? And our arteries, and something is clogging it. They're not symmetrical, correct?
Right. Right.
Like,
so, yeah. Oh, go ahead.
Sorry, I couldn't hear you.
Oh, yeah. You're right. So it's if you have some disease in the vessel, then you might not have a symmetric velocity profile. And so these assumptions that we're making right here, these are for kind of very basic flow in a tube, basically. And the tube has the same diameter all across. And so this obviously won't apply to some more complex situations where you have stuff clogging your arteries. Or even unsteady flow, which is pretty common, which is common everywhere in your cardiovascular system. But this is kind of just a starting point. So with this, we're going to solve for a velocity solution, and then we're going to basically use that as kind of a launching point for talking about a lot of other stuff. Yeah.
Got it. Thank you.
Yep. All right. Any other questions on this before we start solving the Navier-Stokes equations? Okay, and so now that we have all of our assumptions and we have our boundary conditions, we can go ahead and start solving Navier-Stokes. Okay, and this particular solution of Navier-Stokes, which is flow in a cylinder that's not hollow, so it's a solid cylinder, subject to a pressure gradient. This is a very famous solution, and it's named after the guy who first solved it, or in this case, the first two people. And so this is called Hagen-Poiseuille flow. Okay. And so it's Hagen, like Haagen-Dazs, and then Poiseuille flow. Okay. And so anytime you hear Poiseuille flow in fluid mechanics, what that basically means is that the flow is being driven by pressure. So it's any kind of internal flow driven by pressure. Okay. And so the geometry for the Hagen-Poiseuille flow looks like this. Right? And so we have a cylinder just like this. Okay. On the cylinder, we're going to have a pressure gradient. Okay. And so we're going to have P1 on one side and P2 on the other. Okay. We have a length of the cylinder given by L. Okay. And if P1 is greater than P2, and so we have a pressure gradient going down the length of the vessel, then we're going to have flow. Okay. Right. Question. All right. And so one other thing, we have the radius, right? And so the radius of the cylinder, we'll give it big R, okay? And then the other thing that I'll write down here is our coordinate system. Right? And so you can see here we're in cylindrical coordinates. And so down the length of the vessel, we'll call that the Z direction. And so that's our axial component. And then perpendicular to that is the R direction. Okay, so the R is the kind of the radial direction for our coordinate system. Okay, all right. And so what we're going to assume in this case, just like we stated in our assumptions, is we're going to assume that the flow is purely in the axial direction. Okay. In other words, the flow is only going to be in the Z direction. Okay. Okay. And so since we're solving a cylindrical problem, we need to have Navier-Stokes in cylindrical coordinates. Okay. And so I'm going to write down basically the Navier-Stokes in cylindrical coordinates, and then we'll go through and cancel the terms based on all of our assumptions. Okay. All right. So first, let's start with our continuity. Okay. And this is going to be in cylindrical coordinates. Okay. All right, so our continuity equation looks like this. So we have 1 over R. We have partial R times R UR, okay, plus 1 over R partial theta of U theta, okay, plus partial UZ partial Z, okay. And so even though it looks different than our Cartesian continuity equation, you can see it has kind of the same components, right? And so we have one term for each of the velocity components. And so instead of UV and W here, we have UR, which is the velocity in the radial direction, U theta, which is the direction in the polar direction, and UZ, which is the velocity in the axial direction, okay? Okay, and so let's simplify this with our assumptions, okay? And so if we assume that the flow is purely axial, then we know that UR and U theta are going to be 0. Okay? Right? Because if UR and U theta were not 0, then we wouldn't have one-dimensional flow. Okay? And so let's go ahead and cancel out the terms in this equation that have UR and U theta. Okay? Right? And so the first term in this equation is going to go away because that one has UR. And then our second term in the equation is also going to go away because it has U theta. Okay. All right. And so what we end up with from the continuity equation is that duz dz is going to be equal to 0. Okay. And so basically what that states is that the velocity is not going to change in the z direction. Okay. And so another way to basically state this is that the flow is going to be fully developed. Okay. Okay, and so this by itself, we won't be able to use it right now, but we'll use this later in helping us simplify the momentum components of Navier-Stokes. Okay. All right. Any questions on this? Okay. Yeah. And so that last part, I was saying that if you have duz dz, what that means is that the flow is fully developed. And so what that means is that as you progress down in the z direction, and so as you go down the cylinder right here, the velocity is not going to change in that direction, right? And so if you consider one location here on the left, we'll call this location 1, and you consider location 2 a little bit downstream of that on the right, then the velocity is not going to change between those 2 points. Yeah. It's not that it's constant, and so we'll see that the velocity it's going to depend on r. But what this tells us is that the velocity does not depend on z. Yeah. Yeah. Mm-hmm. Okay, and so that's going to help us out. So so once we get to the momentum equation, any derivatives with respect to z, we're going to cancel that out of the equation. Yeah. Top of the velocity profile. And so what do you mean by top of the velocity profile? Okay. Yeah. So yeah. So whenever you have fully developed flow, that just means that as you go in the same direction of flow, the velocity is not going to change. Okay. I'll draw a better picture of that later on once we actually finish solving the whole thing. Okay. Okay. And so now let's go ahead and move on to the momentum part of Navier-Stokes. Okay. Okay. And so I'm going to write the momentum Navier-Stokes in cylindrical coordinates. So this guy is a little bit of a beast. Okay. In particular, I'm going to do just the axial component of the momentum.
If I'm at the bottom of a page in my notes, should I flip my page?
Yes. that would be good. Okay. All right. So let's go ahead and write these out. So even though it looks scary because it's cylindrical coordinates, you'll see it has all the same features as our Cartesian Navier-Stokes. Okay. And then I think he was just asking because it's going to be a lot of writing, so you don't want to start. You want to start on kind of a fresh page on this guy. Yeah. Okay. Right. So that's the entire left side, and so that's the unsteady term and the convective terms. Right? Okay. Here we have the pressure term and the gravity term. And now let's write the viscous term here. Okay. All right, so we have mu over rho. This is the part that I can never memorize here. So it's going to be 1 over r. If my stylus will cooperate. Okay. 1 over r times partial r times r partial uz partial r, okay, plus 1 over r squared partial squared uz partial theta squared plus partial squared uz over partial z squared. Okay. 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 For some reason, that area of my iPad is giving me issues. Okay. And so let's go ahead and cancel out some terms here according to our assumptions. Okay. All right. So first we have the steadiness assumption, right? Okay. And so that first term there with the time derivative is going to be 0. Okay. Next, we're going to cancel out both of these guys for the same reason, or almost the same reason, okay, which is due to our assumption that our flow is one directional, right? And so any term with UR or U theta is going to be 0, okay? We're also going to cancel this term right here because we know from continuity that partial UZ, partial Z is equal to 0, right? And so this is our fully developed assumption, okay? Next, we have gravity. We're going to ignore gravity because, we're going to assume that it's not significant here, okay? Right. Next, we're going to eliminate this term, And if you remember when we were talking about our assumptions, we had our fifth assumption, which was the axisymmetric assumption. And so what that means is that any derivatives with respect to theta, we can go ahead and cancel those out, okay? Right. And then we can also cancel out that very last term right there because it's just another form of duz dz. It's just another derivative of that, right? And so since duz dz is equal to 0, then if we take one more derivative of that, it's also going to be 0, okay? All right, and so the vast majority of these terms are 0 because of our assumptions. And so now what we can do is we can just look at what's left and then solve those guys, okay? All right. And so after we, after the dust clears and we kind of move away all the carnage, all we're left with is this, okay? And so on the left-hand side of the equation, we just have a 0. And so that's the result of canceling out the unsteady term and the convective terms, okay? We have first our pressure term. Okay. And so we keep that guy because pressure is going to be driving our flow. Right? Then we have our viscous term. Right? And so the only surviving viscous term looks like this. Okay. All right. And so this is going to be our starting point for actually solving for the velocity distribution. Okay. And so you can see it's a lot simpler here than what we started with. Right? And another nice feature here is that since we've kind of eliminated any dependence on z and theta, what we can say is that instead of these partial derivatives, we can replace them with regular derivatives. Okay. Right? And that'll make our life a little bit easier when we're performing the integrations. Okay. All right. Any questions on how we arrived at this equation right here? Okay. All right. And so now that we're here, we can actually go ahead and start solving it. All right. So the first thing I want to do is I want to eliminate these densities. Okay. Okay. And that will eliminate density from our equation. Right. Then what I'm going to do is I'm going to move this pressure term over to that side of the equation. Okay. Just so that we have one on both sides. And then I'm going to also multiply by r over mu, okay? And so what that will do is that will eliminate this term from that side of the equation, and then we'll put it on the right side, okay? And then the result of this will allow us to basically more easily integrate this result, okay? Okay. All right, so let's go ahead and do that. And so if we perform those operations, what we get is r over mu times partial p partial z, okay, is equal to ddr of r duz dr. Okay. All right. And so at this point, now what we can do is we can integrate to get rid of this derivative on the right-hand side. Okay. All right. And so if we perform that integration and we assume that our pressure gradient here is not a function of r, okay, Okay. Then we can just simply integrate this guy, pretty simply. Okay. And so the result of the integration on the left is that we have r squared over mu, 2 mu, times dp, dr, or dz, sorry, okay, plus c1 is equal to, the integral is going to cancel out with that derivative, and what we have is r duz dr, okay? And so remember, you have to add a c1 here because we're doing indefinite integrals. And so when you do that, you have to add your arbitrary, integration constant, okay? And so that's where the c1 comes from. From here, we're going to divide by r, okay? And then integrate again. Okay. And so if we do that, we have r over 2 mu times partial p partial z plus c1 over r is equal to duz dr. Okay. All right. And so from here, we're going to integrate one more time, right? And so that'll get rid of the derivative on the right-hand side, okay? Oh, so we're integrating with respect to r. Yeah, good question. So there should be a dr right here. Yeah. Mm-hmm. All right. And so if we perform this integral one more time, we end up with r squared over 4 mu times partial p partial z plus c1 natural logarithm of r, okay, plus c2. And this is our u of z, or u of r right here. Okay. Right, and that's our velocity solution, right? And so now that we have it at this point, we're not done yet because we have to solve for the constant c1 and c2. And the way we're going to do that is with our boundary conditions, okay? But before I do that, are there any questions on how we got to this point here? Okay. All right, so let's apply our boundary conditions and solve for c1 and c2. Okay. Okay. And so the first boundary condition I'm actually going to apply is our symmetry boundary condition. Okay. And so remember, our symmetry boundary condition stated that our derivative of the velocity with respect to r applied at r is equal to 0, this guy has to equal 0, okay? In order to basically give us a symmetric velocity profile, all right? And so let's take our velocity solution, which we have down here, that's boxed, and let's take the derivative once, okay? And so we take the derivative. Again, my r's and my z's mixed up, right? So duz dr, what we get is r over 2 mu times partial p partial z, okay, plus c1 over r, okay? Right? And so this is simply just the derivative of our velocity solution. And so now let's evaluate this at r, little r is equal to 0, okay? And so we basically want to compute the velocity at the middle of our, or we want to compute the derivative of velocity at the middle of our vessel, okay? And so I'm just going to plug in r is equal to 0 into here and here, right? And so what we get is duz dr at r is equal to 0 is equal to 0 over 2 mu partial p partial z plus c1 over 0, okay? And according to the boundary condition, this has to be equal to 0, right? Okay, so let's start to evaluate these terms. Right? And so the first thing that you'll see is that we have 0 over 2 pi over 2 mu times dp dz. And so this is automatically equal to 0 because we have 0 times something. Okay. Right. And next we have, you know, the mathematical paradox, which is, you know, something divided by 0, right? And so we have c1 divided by 0, and then, you know, somehow we have to make this equal to 0 right here, okay? And so, you know, the argument that I typically give for this, I know is very hand wavy. And so, you know, there's a much more rigorous mathematical reason of why we do this. But, you know, the way I kind of explain this is that in order for this to be satisfied, this C1 term right here can't be here. So it just can't exist, right? Right. And so as long as C1 is in the picture, you know, we're never going to be happy, right? So it's like the, you know, it's like a side chick, right? So as long as the side chick's in the picture, you know, you're never really going to have a happy relationship, right? And so same thing with here. And so in order for us to get rid of the C1 term, we have to basically set C1 is equal to 0, okay? Okay. And so, you know, if we set C1 is equal to 0, then this eliminates that C1 term. Okay. And so now it's out of the equation and we don't really have to worry about it, okay? And so if we go back to our general solution here, if we set C1 is equal to 0, then this guy is just not going to be there anymore, okay? Okay. Any questions on this? Okay. So that's the C1 term, but we still have to solve for C2, okay? And so for C2, we're going to apply our no-slip boundary condition at the exterior of our blood vessel. Okay?
Wait, so the C1 term is the equation we boxed before, just without the C1?
Exactly, right. And so the C1 was basically our natural logarithm term right here. And so, you know, we basically are going to say it's 0. So, you know, intuitively speaking, since we have this blood vessel where the origin of the blood vessel is part of the domain, and so we basically have r is equal to 0 is part of this. There's no way for that natural logarithm to exist, because if we take natural log of 0, then we get minus infinity. And so that's, you know, that just can't happen, because you can't have, you know, blood is not going through your system at the speed of light, you know. And so in order for that to, in order to kind of reconcile that mathematically, we just have to say that, you know, we have to eliminate that term. And so mathematically, you can say that C1 is equal to 0. Although right here we have, you know, 0 over 0 in boxed in green. And so that, you know, doesn't really make that much sense. And so the way I kind of like to think about it is that, you know, we just have no dependence on the logarithm at all. So we just kind of get rid of that term just altogether. Yeah. Okay. And so our no-slip boundary condition basically says that if we evaluate our velocity at r is equal to big R, then, you know, our velocity has to equal 0. Okay. All right. So let's go ahead and plug that in. And so now we're plugging it into just the velocity, so not the derivative, but just the velocity itself. Okay. And so if we evaluate uz at little r is equal to big R, what we get is big R squared over 4 mu times partial p partial z plus c2 is equal to 0. Okay. And now from here we can solve for c2. Okay. And we get C2 is equal to minus r squared over 4 mu partial p partial z. Okay. Right. And now that we've solved for C1 and C2, we can go ahead and plug this back into our velocity distribution and then get our final answer. Okay. And so our final answer for the velocity distribution for Huygens-Poiseuille flow looks like 1 over 4 mu times partial p partial z little r squared minus 1 over 4 mu my stylus is tripping out right now. Right, 1 over 4 mu times partial p partial z times big R squared. Okay, we can simplify this and kind of combine them into one big term. Okay, and so we have 1 over 4 mu times partial p partial z times little r squared minus big R squared. Okay. Okay. And there is our velocity solution. Okay. And so this is the velocity solution for Huygens-Poiseuille flow.
Professor, that's a r square minus k square, right?
It's a big R, sorry. Little r squared minus big R squared. Yeah. Yeah, my stylus was kind of tripping out. And this should be Huygens-Poiseuille flow. Okay. All right, any questions on how we got here? All right. All right, so one more thing I want to do before we end today is we can take this velocity distribution and compute the flow rate. Okay. Okay. If you remember from last time, flow rate refers to the volume, the rate at which the volume of blood is kind of moving through your system. Okay, and so it's a volume over time. Okay. All right, and so the way that we can compute flow rate from the velocity distribution is we can just simply integrate. Okay. Okay. Yeah. Sorry, my iPad's kind of just really flipping out on me. Right? All right, and so the formula for that is going to be Q is equal to integral over the area of UZ of R times dA. Okay, where dA here is our integral element for the area, and so for a cylinder or for a circle, it looks like this. And so we're going to integrate from 0 to big R of UZ of R times 2 pi R dr. Okay, and so that 2 pi R dr, that's going to be our dA in cylindrical coordinates. Okay. Okay. And so what you can do here is you can plug in our velocity solution from the previous page and plug it into this formula here to compute the flow. Okay. And so I'll let you guys plug that in to verify that because I kind of want to make another point. But if you plug in that velocity distribution and you perform the integration, what you get is Q is equal to minus pi over R to the 4th divided by 8 mu times partial P partial Z. Okay. Okay. Man, what is wrong with my stylus today? Okay. And so that's the flow rate. Okay. Okay. And so this is fine right here, right? But let's simplify this a little bit more. And in particular, let's simplify the pressure gradient term. Okay. And let's put this into some some more plain variables, because having that kind of derivative term out there kind of is a little bit of an eyesore. Okay. All right. And so to replace that, let's remember our problem of geometry. Right? Right, so if you remember from our problem geometry, we had a tube where the two ends of the tube, one of them was held at a pressure P1 and the other end was pressure P2, right? And then the length of the tube we'll say is L, okay? All right. And so what we want to do is we want to approximate this pressure difference, or approximate the pressure gradient using these terms, okay? And so what we can say here is that, we can say that minus dP dz, okay? This is going to be equal to the difference in pressure between, the inlet and outlet of this tube. And so we'll say that this is P1 minus P2, okay? All divided by the length, right? And so that's what the derivative represents. So the derivative, remember, represents a change in pressure over the change in length, okay? And so we can approximate that by literally putting the change in pressure, which is P1 over P2, over length, okay? And then, and just to kind of make this a little bit, easier to write, instead of writing P1 minus P2, we can represent that as delta P over L, okay? Where delta P right here, this is going to be our pressure difference. Okay? And so delta P is going to be P1 minus P2, okay? All right. And so now, now that we have this relationship, we can go ahead and plug this in for dP dz, and then we can form an important relationship that will we'll actually see more and more in the weeks to come. Okay. All right. Any questions on this? So the question is it still high to low direction of flow? Yes. Yeah. So the flow is still going to go from high pressure to low pressure. Yeah. So we're just replacing that that derivative with some kind of raw values in there. Yeah.
So that negative would go away?
Yes, exactly. Yeah. So we put this negative out in front here as kind of, to kind of represent that fact, because the flow here is actually negative out here, but the pressure gradient is actually ends up being kind of a negative number itself. So those two things kind of cancel out. And just so that we don't have a negative kind of floating around in our solution, we kind of just cancel it out here. Yeah. Because ultimately what we want to get from this is a relationship between pressure and flow in a cylindrical vessel. And that's going to be our starting point on Thursday. All right. And so if we plug that in, what we get is Q is equal to pi over r to the fourth over 8 mu, okay, times delta P over L, okay? And so let's take this expression and solve for delta P, okay? And so what we get is delta P is equal to 8 mu L over pi big R to the fourth times Q. Right? And so this equation is going to be significant because this shows the relationship between pressure drop and flow rate in a cylindrical vessel. Okay. And so this is going to be significant because it'll help us come up with this concept of something called a resistance. Okay. And so that quantity that I have in parentheses there, you can almost think of it as like a resistance to flow, right? And so if you have a certain pressure difference, depending on the resistance of your vessel, that's going to change the amount of flow that actually gets developed. Okay. And this idea of like a resistance to flow is something that's used a lot in cardiovascular fluid mechanics. Okay. So this is kind of the first taste, but we'll be revisiting this concept, over and over in this class. Okay. All right. So are there any questions on this before we sign off for today? Okay. All right, so if there's no questions, that's all I got planned for today. And so thank you guys for coming in. So sorry, I was a little bit frazzled today because I was kind of figuring out my internet at the beginning of class. But hopefully this class today was a lot of refresher from your fluids class with a little bit of a wrinkle because maybe not everyone does cylindrical coordinates for Navier-Stokes. So there you got a little bit of a taste of that there. Okay. All right, so on Thursday we're going to pick this up and we're going to see how this relates to an important law in cardiovascular fluid mechanics called Murray's law. Right. All right, so thank you guys for tuning in today. Have a great rest of your evening, and I'll see you on Thursday.
Thank you.
Yeah,
Professor, I have a quick question for 410.
Yeah, what's up? Mm-hmm.
When you say for one of the questions to calculate the ratio between the elements, how do you do that?
What's that again?